getting started here.
Hello.
Hello. Oh, I like your piano.
I don't know if you remember me. I joined your meetup a while back and was mostly listening. And I don't have a physics background, but I would very much like to lurk a bit and listen to what you guys have to say. If you don't mind, it definitely sounds interesting what I'm going to talk about today.
Yeah, sure thing. Yeah, you're definitely welcome.
Thanks.
Good morning, everyone.
Oh,
Good afternoon.
Matt, can I ask my ignorant questions up front?
oh yeah, please.
You know, I read your notes, and I also read some other papers on the Wigner quasi-probability distribution. I don't get it. I don't see what the point is. It seems to be inferior in all respects. It's inferior to the wave function analysis for quantum physics. And in my field, electrical engineering, where I know something about signal analysis, it seems to be inferior to the fast Fourier transform, which is the standard way of spectrum analysis of a waveform. What's the point? What am I missing?
Yeah. Well, okay, so I think there's like a couple answers. I mean, I think that one is maybe philosophical. You know, people are sitting around trying to be like, hey, can we generalize joint probability distributions to the case of like non-commuting quantum variables? Okay, that. But then, you know, the other thing is that, for example, you know, at some point in here, I show how to construct very easily the Wigner quasi-probability distribution for a Gaussian state. And, you know, you look at it, it's just like this exponential. And, you know, when you go to integrate Gaussian functions, it's like it's super easy. So like in that representation, it's going to be like really sort of easy to evaluate things if you can do Gaussian integrals.
Easier than just using regular Schrodinger wave function analysis?
Yeah, I mean, potentially. I mean, the other thing is that, you know, so I give a little expression that allows you for a Gaussian state, as I say, like how to just easily construct the Wigner quasi-probability distribution. And so it's like, you know, we'll see, like, when we talk about the Gaussian stuff, that Gaussian states are very easy to characterize. They're just characterized by their first and second moments. It's just a vector in a matrix. And from those, you just sort of plug it in and get the Wigner quasi-probability distribution. So, I mean, I don't know all of the interesting reasons why people might be into the quasi-probability distribution, but certainly, you know, if you're working with Gaussian states, it like makes things easy.
Well, of course, you know, as an engineer, I'm interested in the practical applications, and there have been practical adaptations. Glauber, Nobel laureate, and graduate of the first class of Bronx High School of Science. He's no longer alive, though. He adapted it to spectrum analysis and, you know, and signal analysis. But from what I've read, it seems to be inferior to the fast Fourier transform. But let me ask you something else.
Oh, well, the coherent state thing, I mean, it's more akin to like, so far as I understand, like a wavelet transform.
Well, it's used in quantum optics. I know that. It has advantages. I'm not sure I understand. I need to do more reading. But let me ask you something else. You know, I'm an adherent of de Broglie-Bohm pilot wave theory as opposed to Copenhagen theory. In my readings, I came across a hint that the Wigner approach can be related to the to Bohmian mechanics.
Yeah, I think I saw that too. I can't really speak to it, but I do remember it, yeah, in a paper or two. So people.
Because, Bohmian mechanics gives you actual physical trajectories of quantum particles. And apparently some, mathematical deformation of the Wigner function can be related to, pilot wave theory, Bohmian mechanics.
Yeah, I could certainly see that. Yeah, I'll look up some of those papers. Maybe next time I'll have something.
Yeah, I know this is not your field of expertise or interest, but I was just curious because I came across it. But then I read another paper that said it has nothing to do with pilot wave theory. So I'm all confused.
Well, I think, like certainly in spirit, right? Like this idea of both in like the sort of Bohmian theory, being able to like assign position momenta to these
right.
Little particles that are like really existing here. You're sort of assigning joint probabilities to, position and momentum. So yeah, like definitely in spirit, like certainly like when you imagine Wigner or whatever coming up with it, he was like clearly in the mindset, like trying to stick as close to
well, apparently a number of people, even preceding Wigner, Dirac, for example, who was his brother-in-law, came up with it. But
yeah, okay, yeah, I think that's
Dirac was married to Wigner's younger sister.
Crazy.
But apparently Dirac did not understand the significance of what he had discovered. And apparently Wigner and Dirac never even discussed it, even though they were brothers-in-law.
He didn't understand the significance of what?
Well, that's what I'm asking, because I don't understand the significance of the whole thing, except that it's a phase space analysis, as opposed to wave function analysis. And again, I don't understand the advantage, and there doesn't seem to be an advantage in most cases. So that's what I'm here to find out.
Well, again, as
we'll
on
the spot, Matt.
As we'll see, from what I understand, I'm sure there's more to say about it. Particularly when you're working with Gaussian states, it's just the Wigner representation is just very nice and easy to work with.
Can you define, again, that's another thing that's a little confusing to me. I mean, we all know what a Gaussian distribution is, but specifically, I'm not sure if you covered this before, but I was probably nodding off. Specifically, define a Gaussian state in this particular context.
Okay, well, maybe I'll hold off like a little bit on that, just because we'll come to that. But just to say something now, right? It's the vacuum state of an oscillator is naturally a Gaussian. So you can imagine taking that Gaussian and displacing it in position or momentum, and then you get these like displaced or coherent states. Just another way of talking about coherent states. You can also take the Gaussians and squeeze them. And, you sort of like squeezed in position, it gets fatter in momentum, sort of a trade-off there. It's like a normal Gaussian, like the way that you think of it. And so, So
you're referring specifically to a quantum harmonic oscillator.
Yes.
Right? Okay.
Matthew, what you described right now doesn't sound to me like a vacuum state. It sounds to me like you have a particle there.
It's, you can think of it like those displaced states as like a displaced vacuum state. Well, so instead of being centered at the origin, it's just somewhere else.
But then the quantized energy levels are still the same.
It's, both, sort of, yeah, I mean, it's going to be a superposition of energy levels. Yeah, I can't remember the exact.
Although the Gaussian, the states are continuous, but the energy levels are discrete. That's my understanding.
Okay, well, we got a good crew here, so let's get started. I'm going to share my screen. So before we get to the Gaussian stuff, let's just talk a little bit about like this negative probability idea. So, you know, on the surface, it's like negative probabilities. What are you talking about, you know? So as usual, there's a quantum mechanical twist to the idea here. And so, you know, we're used to the idea in normal probability theory of forming a joint probability distribution of two random variables. But, you know, suppose we're working in a quantum mechanical context. And we're like, hey, I want to construct a joint probability distribution for both position and momentum. But hey, position, momentum don't commute. You can't know them both simultaneously with complete accuracy. So you might imagine that's probably going to throw some kind of monkey wrench into the machinery. And that's true. So the quantum generalization of the joint probability distribution, it's called a quasi-probability distribution. And on the one hand, it's really quite like a joint probability distribution in that, you know, in the case of these Wigner functions for position momentum, you know, it's a function. It's a function of possible positions and momenta. And if you integrate over momenta, you just get the usual probability distribution for position. And if you integrate over positions, you get the usual probability distribution for momentum. So in that sense, it's just like a normal joint probability distribution. But the twist is that the quasi-probability distribution itself can take negative values. So you can try to, you know, interpret these in different ways, okay? And some papers that you'll read will try to get a little philosophical about, well, what does a negative probability mean? I think, you know, I can't remember which paper this was in, but someone had like a funny example where they're like, well, and I don't know if this really generalizes, but they were like, okay, so you know, you have a text and you could count up the number of letters in it, you know, be like, oh, you know, 50% of them are A's or whatever, 12% of them are B's. But, you know, suppose you're considering like a typo, okay? Then, well, and I guess in this case, you'd be sort of maybe assigning probabilities to words, not letters. So, you know, the number of times a word appears in a text, you get a probability for it. And then like, suppose, you know, the word skip, but you misspell it, S-K-P-I, okay? And then like the spell checker corrects it. And so like it never appears in the text itself, but if you wanted to assign like a probability for SKPI being a word that appears in this document, maybe you should assign it a negative probability because, you know, you could be like, well, you know, it could appear, but then it'll be corrected. And so it like won't appear. So I thought that was kind of a funny way of thinking.
Matt, can I ask a question? Can I ask you a question?
Mm-hmm.
Why can we not interpret this negative probability as a conditional probability? In other words, the Venn diagrams are overlapping. The probabilities are not independent.
Yeah, so I mean, that is sort of kind of basically like the idea, yeah, in the end.
So why is it such a big deal?
Well, it's sort of like, you know, similarly, you know, to complex numbers where, you know, it's like we never measure an amplitude directly, we always measure a probability. Similarly, it's like, well, what do you mean? How do you test this thing has a negative probability? I mean, if all you're doing is just measuring the frequencies of outcomes, obviously you're never going to get something negative out of an experiment by definition. So as I say, people have spent, you know, some time trying to like think about, you know, how to interpret negative probabilities. And, you know, they're like all sort of more or less convincing. But similarly to complex numbers, you can just sort of view these negative probabilities instrumentally. You know, they just cancel out in the end, but they're really useful in the intermediate steps of the calculation. The upshot.
But I guess you're going to show us how those negative probabilities come in.
Yes, we will.
Okay. It
So,
is not because someone had an indigestion.
Yeah, yeah. So I'll show you an example of how they can come up when we're talking about a qubit, and then we'll talk a little bit about the Wigner distribution itself for position momentum, which is like the most famous example.
Matt, another question. You know, in the Klein-Gordon equation, the way negative probabilities are dealt with is that they are annihilation operators.
Right.
Is there any relationship with that to this, or is it completely different?
I don't know. Maybe. I'm not sure. There might be a way to connect it, but I don't know. But you know, one interesting thing, as I was saying about these quasi-probability distributions, is that they actually provide like yet another way of formulating quantum mechanics. Like you can work with quasi-probability distribution, you know, with no loss of generality. Anything you can do with a wave function, you can do with these guys. And I like it because, you know, quantum mechanics, one of the things that's attractive about it, to me at least, is it's sort of protean character. I mean, there's a lot of ways, like as we well know. You can work with the Bohmian trajectories, you can work with, you know, your state vectors, you can work with your quasi-probability distributions. There's a million ways of talking about quantum mechanics. And each sort of has their selling point. Okay, so let's give like a simple example of like how are we going to get these negative probabilities just in the very simple case of a single qubit. So as we well know, the Pauli matrices don't commute. And so there's a intrinsic uncertainty associated to a qubit's rotation axis. Yeah. Classic example, we measure the spin along the x direction, and then it ends up in an x eigenstate, which in terms of z eigenstates is up plus down, or the other one is up minus down. And indeed, notice like those x eigenstates are both superpositions of z eigenstates. So if we measure the spin along the x direction and then measure along the z direction, we're always going to get 50-50 up or down. A definite value of spin along the x direction precludes the spin from having a definite value along the z direction. But what if we were like, whatever, I still want to define a joint probability distribution for the spin to be up or down along the x-axis and for the spin to be up or down along the z-axis. So here's one way to proceed. And this construction is kind of funny. It's kind of like a little trick. I believe something quite like it is originally due to Feynman. And at the end, I have a little bibliography, and there's a nice paper that he wrote just called Negative Probabilities. And so you could read that. So here's our z eigenstates, and here's our x eigenstates. We can consider the projectors onto these eigenstates. You know, we can write it out in bracket notation. It's just a little outer product here of the eigenstates. And I've just given, you know, the matrix representation of them. You know, we can use these projectors to get the probabilities for a given state to be one of the eigenstates. So if we have some qubit state psi, then the expectation value of psi on the projector gives the probability. So it could be like probability that z is up is, here's the projector, and we wedge it in between the psi, the qubit state. And you see that this is just going to be the amplitude squared, as usual. Now, another way of writing out these projectors is like this. You can write the z up projector as 1/2 plus the identity plus Pauli's z. And you could write the z down projector as just 1/2 times the identity minus Pauli's z. And just, you know, for concreteness sake, I've written them out. And you can see that we get exactly the same projectors from before. Similarly, for projectors onto x plus and x minus, we can just have like identity plus x and identity minus x, okay? So now let's engage in a little chicanery. You know, what we're about to see is something that is not unique, right? Okay, there's going to be like a lot of ways that you can pull similar tricks. So just, you know, you'll see what I mean. There's some arbitrariness here, but we get the result that we want in the end. So I'm going to define a projector. I'm going to call it projector onto the, okay, now technically it's not a projector. All right, a projector, if you square it, it gives you itself. This does not have that property, but like, let's bend the rules a little bit, okay? We're gonna call it like a projector. And that bending of the rules is basically the thing that's going to give us the negative probabilities, okay? So we're going to call this a projector onto z plus and x plus. And then we're going to form one that's like z plus and x minus. And what we've done here is I've just taken the projector onto the z plus state, and I've added Pauli x, and I've subtracted Pauli x. Okay? Now, obviously, just by construction, if I add these two together, I'm just going to get the projector onto the z plus state. I add these together, then it's like the plus x cancels out with the minus x. They each have a factor of a quarter, so then when you add them up, you get a half, which is exactly this. Similarly, we could define like a projector onto z minus x plus and z minus x minus. Here, I minus z, that's just, we can see the projector for z being down. And similarly, we just add x and subtract x. And obviously, again, like by construction, like you add those up.
Matt, can you go up a little bit?
Yes.
Okay, let me just look at it a minute.
Mm-hmm.
You say when you take the projector z up, x up, you add it to z up, x down, the quarters disappear, you get 1/2 plus 1/2. That's 1 with 1/2 in front of it. Can you go up a little bit more?
Mm-hmm.
And you said that what you're going to get is the same as the z plus projector, but I'm not sure you get the same thing. At the end of it, what you have on the right side is a 1 in the upper left corner, right?
Yeah.
And when you now go down a little bit, when you add the up and the up down, you're going to get 1/2 altogether.
No, because see, if you just add these two matrices together, a quarter here cancels out with a quarter here.
Yeah,
and then
okay. I just, in my mind, I counted the 1/4. The 1/4 is not there. Okay, sorry.
Yeah, it's already incorporated in there. Yeah, I see what you're
I can't.
Yeah, similarly here, you just add these together. These cancel, 1/2 plus 1/2 is 1, and you just get this guy. So, okay, but it's also the case that if we take z plus x plus and add it to z minus x plus, we just get x plus. So, here we've basically the projector onto x plus is I plus x, right? And so here we've just added and subtracted z. And naturally we get that. Oh, this should be a half.
But Matt, of course, this is all non-physical because spin and orthogonal directions are completely independent. They have nothing to do with each other.
Right. Well, so that's sort of how the negative probabilities are going to come in. Okay. So, the expectation value of a sum of operators is just the sum of the expectation values of those operators. So what that means is that we could kind of rewrite this just completely in terms of probabilities. And so what this is saying is the probability that z is up is the probability that it's z plus x plus and z plus x minus. And so you see here, both of these has z plus, and we're sort of summing over x being up and x being down. Here, for the probability that z is down, these are both z down, and then we're summing over x plus and x minus. Similarly, for x plus, both of these are x plus, we're summing over z plus and z minus, and so on for the next one. And so, this looks just like we're dealing with a joint probability distribution, specifically a joint probability distribution over two variables, x and z, each of which can only take two possible values up and down. The probability for a given value of z can be found by summing over possible values of x, and the probability for a given value of x can be found by summing over possible values of z. And if we add these all up, obviously we're just going to get the identity. And so these probabilities here, these that you get, are going to sum to 1, just like a normal probability. So it seems like we've done our thing. We've somehow managed to define a joint probability distribution for both x and z values of a qubit. But what's the catch? So check it out. So here is just some code. These are just the projectors onto the x and z eigenstates. Here's our 4 quasi-probability operators that we just sort of defined. And here's some code. It takes a qubit, and it it gives us the expectation value of the quasi-probability operators on that qubit state. And you can see that we get the probability for z plus by just adding up these two quasi-probabilities, probability for z minus by adding up these two, and adding up all these probabilities gives you 1. Okay, nothing so strange here. Everything looks fine. Let's keep running.
Matt, how come z plus and z minus have different probabilities? Shouldn't they both be 1/2?
No, so I just start with a random qubit state.
Oh, okay.
Totally. So I ran it until I got the result I wanted here, which is hey, oh shit, this quasi-probability is living up to its name as a quasi-probability because it's negative. And that's the thing. These can take negative values. They still sum to 1. You add it all up, you get 1. In that sense, it's like a probability. Furthermore, if we add these up, we can get our familiar probabilities for z plus, z minus, x plus, and x minus. But these individual guys can be negative.
Wait, I don't understand how you added and to get 1. It looks like there's more than 1 here.
So these 4 numbers added together will give you 1.
Oh, those 4.
Yes.
Z plus, Z minus.
Mm-hmm.
Okay.
And then, but again, how do we know that there's not overlap, that the probability of one of those is not independent of the probability of another? The Venn diagrams overlap.
Yeah.
That's how you would normally interpret, a negative.
I think that's fair. I think that's a fair way to look at it. Yeah.
So again, what's the big deal?
Yeah, it's just another way of proceeding. Okay. So
because again, the whole thing is non-physical. It's even non-mathematical because spin and orthogonal directions are completely independent.
Well, or you could say they're...
Before we continue, there are 2 things here that bothers me.
Okay.
The first one, if the probability sum up to 1, and one of them is negative, then if you sum the rest of them, then you have something bigger than 1.
Yep.
So you have some three probabilities, and it is bigger than 1.
That's exactly right.
The probability of being in one of those 3 states is bigger than 1. How is this possible?
Because they're not independent. They're not independent probabilities, Moshe.
And number 2, how come the probability of z plus x minus is negative? It is not negative. It is, you have a finite probability of having z plus and x minus. So those are the 2 things that puzzle me here.
Yeah. So again, it's like the qubit can't be in that state. There's no such qubit state, z plus x minus. Those are mutually exclusive things, and indeed, therefore, you might say, the probability can be negative.
Same thing for z minus x plus. Those are equally mutually exclusive.
Well, they're not. I mean, they're not like. Well, okay, you got to be careful what we mean by exclusive, right? Like again, like z plus is one thing, and then x plus is z plus plus z minus. So like they're not. They're like they're not independent of each other. To use the word exclusive is like to say like when you think about a measurement, right? It's like to get if you get this one possibility, then you go do the other measurement in the x direction and you get something random, and so we say they exclude each other in that sense.
But Matt, they are all mutually exclusive. Even the positive values are all mutually exclusive, because you measure spin in the x direction, there is no way to give a probable, well, there's no way to, it's completely independent of what's measured in the z direction. So whether you have a positive or negative probability, they're all mutually exclusive.
Wait, say that again?
All of the probabilities are mutually exclusive, whether they're negative or positive.
Well, well, again, what do you mean by exclusive, right? So like the probability
because the probability of spin in x direction is completely independent of the probability of spin in z direction.
In an eigenstate, obviously like in some arbitrary qubit state, you could sort of like project it onto x, project it onto z, and then you get different probabilities or like whatever. Again, it's like probability for getting z up and a probability for getting z down. They're exclusive in the sense that if you add them together, you get one. So it's like you measure along the z direction, it's like either up or down. Similarly, you measure in the x direction, it's like either up or down in the x direction. But
so the thing is, if you have a superposition state that is neither in the x nor z position, this theoretically gives you the probability of measure. But the thing is, you can't measure in the x and z simultaneously.
Yeah.
So what does this even mean?
Exactly. I mean, these are all like valid concerns. Yeah, it's like, okay.
Matthew, let me try to reinterpret what you said right now. Go back to the definitions of 1 plus x minus z and so on.
Mm-hmm.
Yeah, right. Yeah, sort of a little bit further down. Go down a little bit further down. Yeah. Okay. Here where you have p z up, x up, p z up, x down, and so on. Those are definitions. You can define anything you want. Once you have defined something, you can give it any name you want. You call them quasi-probabilities. Okay, so those are the definitions of the quasi-probabilities. Now, you start to explore the properties. First thing that you notice is that quasi-probabilities are not probabilities because they don't square up to 1. Second thing you notice is when you add them together, they do look and feel like joint probabilities. You integrate over x, you get z. You integrate over z, you get x.
Yeah.
So even though they're not probabilities, they do have some properties of joint probabilities. Now,
yeah, that's exactly right. That's exactly my point.
At the point that they are not probabilities, you notice that they can have negative values, which is definitely not possible for a probability.
Okay, so, but as I said, the way they are defined mathematically is what's giving you the negative probabilities. The way they're defined mathematically is telling you that they are not independent probabilities. That's why you're getting the negative. There are overlapping Venn diagrams. But again, in the physical world, this can't exist.
So I mean, basically, one can like rack one's imagination to try to like be like, well, what does it mean? Question really is, for a physicist, is it useful? And that's where we're going to come to. Okay. So let's move on to.
That's what we're waiting for, the usefulness.
Yeah. Okay. So that's just, I just did the qubit example, just to kind of like as a warm up. So now let's talk a little bit about the Wigner quasi-probability distribution for position and momentum. I'm going to give just like some definitions here. Basically take it from the Wikipedia article. We're not actually going to really like use these like that much for reasons that we'll see, but I thought it would be good just for concreteness. Like, what are we talking about? So, suppose you have some position wave function, okay? You can define its Wigner quasi-probability distribution of position and momentum by using this sort of Wigner transform, okay? So, you look at it and, it's like psi conjugate times psi, and you're integrating over f, and you got this little exponential there. Let's not worry about too much, what does it mean? We're just looking at it. Like, okay, see, something's going on there. Similarly, if you had a a momentum wave function, you could define it in terms of that. But the crucial fact is that, if you take such a quasi-probability distribution, we integrate over momentum, boom, we get the probability distribution for position. Similarly, we integrate this guy over positions, boom, we get the probability distribution for momentum. And that's the whole thing. So similarly, you can calculate the overlap between states, solely in terms of these Wigner functions. So, you have the Wigner function for some state alpha and some state beta. And, you just sort of multiply them together and integrate over both position, momentum. Boom, you get your probability, for the overlap between alpha and beta. Similarly, if you have some operator, you can sort of Wigner transform the operator into this representation. So, you basically integrate over some f, and, you're taking this little inner product with all these different possible f's. And, you end up defining this function g of x and p, given some operator g. And then you can calculate your expectation value of psi on g, similarly to here, where you just sort of, multiply the Wigner function for your state by g. Oh, that should be a psi. And there you go. So, that's just to give you a sense of like, okay, this is some of the machinery. There's gonna be these integral transforms, and things that we care about, probabilities, expectation values can all be calculated, using these Wigner functions. Now, luckily, like, we're not actually going to use this too much because we're going to be working with Gaussian states. And so we're going to sort of be like directly working with a Wigner function. We're not actually going to like transform some wave function. Just, you could, but like, we're just not going to do that today. And also we're going to be using Xanadu's awesome library, Strawberry Fields, which actually just has all this Wigner stuff built in. So we're going to do it by hand, and we're also going to use their functions for it as well, and they make it super easy to work with. And I mean, so Xanadu, they're building like a photonic quantum computer, and basically, sort of as Michael was implying with these Glauber, coherent states and stuff, Wigner quasi-probability distributions, very popular in the quantum optics community. So let's look at some Wigner probability distributions, like specifically for Fock states. In other words, states of an oscillator with a definite number of quanta. So again, we're going to use Strawberry Fields. So
Matt, would you say a Fock state is the opposite of a Gaussian state? A Fock state is discrete and Gaussian is continuous.
Well, that's not exactly the distinction. So I mean, the vacuum state is Gaussian. The other Fock states, the other states of definite number, are most assuredly not Gaussian. The Gaussian states in general are going to be superpositions over different numbers.
Wait. You say the ground state, the vacuum state, is Gaussian?
Yes.
For a harmonic oscillator?
Mm-hmm.
But it's discrete. It's not Gaussian.
The discreteness is sort of, in the eye of the beholder, right? It's, from the perspective of a wave function, right? You have like, you can evaluate that at a continuum of values. But if you describe it in the energy basis, then you can describe that as like a bunch of amplitudes for each energy state. So it just depends on your representation.
The energy states are discrete, but what states are we talking about?
So
The state?
yeah, the state
And
with,
I think what you mean is when you look at the Schrodinger equation, you have a set of eigenvalues, and the eigenvalues are discrete. Once you pick an eigenvalue, use an eigenfunction corresponding to this eigenvalue, but the eigenfunction is a continuous function.
yeah, so like
What you mean?
in the energy basis, the eigenvalues are just like 0, 1, 2, 3, 4, 5, and the eigenstates are the states of definite energy. But if you consider that same thing like in terms of like a wave function, and you're sort of describing it in terms of like eigenvalues and eigenvectors of like the position operator, then you have a continuum of eigenvalues, one for each position, and then the eigenvectors are those position states or momentum states. So so basically, all right, so we import strawberry fields, okay? So here's sort of like, this is very simple, okay, a very trivial kind of strawberry fields program here. We define a program with one oscillator mode. This is the thing about strawberry fields. It's like about oscillators, right? So like, if you were using Qiskit or like some other thing, that's qubit based, this would probably mean like, I'm gonna create a circuit with one qubit. Here, this means I want a program with one oscillator mode. And then we can define the program. We sort of define like a context, and which is basically going to give us a sort of Q is going to be like our modes. And we prepare a Fock state on the first mode. Then to actually run the program, we use their local engine. There you have different backends. So here we're using the Fock backend. Later on, we're going to be using their Gaussian backend, which is just like makes, simulating Gaussian states super fast. All right. But when we use the Fock backend, we have to set a cutoff dimension. In other words, we're not going to allow just arbitrarily high energy levels or arbitrarily large, number states, because that would be painful. So we have our engine, we run the program on the engine, and then we're going to visualize the Wigner quasi-probability distribution. So, we just sort of set up, a bunch of X and P coordinates, and we can just use their built-in function to evaluate the Wigner quasi-probability distribution at each of those values, Q and P, and then we plot it. So actually, let's just look at Fock 0. So there it is. There's the Wigner quasi-probability distribution for the vacuum state. All right. Here's the position axis. Here's the momentum axis, and you see it's very Gaussian. It's very Gaussian looking thing. Okay. So then that's cool. Let's look at the first number state. Oh, look at that guy. We suddenly are aware that this shit can go negative. Here's 0. And we have some values that are lower than 0. And actually what we'll see is that in general, like I'm saying, quasi-probability distributions can be negative. But specifically for Gaussian states, they're not. So Gaussian states always have positive quasi-probability distributions. And in fact, that's one way of characterizing them. And indeed, that's one of the, I can say that, here's the vacuum state again. And indeed, its quasi-probability distribution is like totally positive. On the other hand, like let's look at, the second number state. Look at that guy, kind of funky. And it's so like negative over here. So, you know, and like the different number states here, let's like amp this up, like the A, you know, let's look at like, you know, number state with 6. And, you know, the general trend is like, you know, there's more ripples, the more ripples you get for the higher number states, okay? So that's cool. Just give a little intuition, a little visualization. Okay, so that's the intro to that. So now let's like talk about the Gaussian stuff, like specifically, okay? So like I was saying, now this is the thing, right? You might be like, hey, you know, there's classical simulation, there's quantum simulation, and, you know, it's really hard to simulate quantum mechanics on a classical computer. And you might think something like, well, it's because of the entanglement, right? Like quantum states, they get all entangled, then they're difficult to simulate classically. Well, that's actually not always true. So Gaussian states, like multi-mode Gaussian states, can be super entangled, but they can still be efficiently classically simulatable. And that's just the fact about Gaussian states. They're really easy to simulate classically. And so for example, like Strawberry Fields has this like super optimized backend for doing like rapid calculations specifically with Gaussian states. Another thing to know about Gaussian states, like I'm saying, is that, you know, their quasi-probability distributions are never negative. And maybe, you know, is that something to do with why they're classically simulatable? Maybe. So the essential fact about Gaussian states is that they are fully characterized by their first and second moments. Like for general states, you know, you might need arbitrarily high moments, third, fourth, fifth, whatever. But Gaussian states are like fully characterized by their first and second moments, okay? So what's a moment, all right? So like, let's go into that. Suppose we have n oscillators. Each has a position and momentum operator. And so let's form a 2n dimensional vector out of those operators. It's like a vector of operators, you know, and you can sort of, by convention, like organize this in different ways. And if you read different references, they organize it in different ways. But the way we're going to do it here to make it like consistent with actually Strawberry Fields is we're going to put like all of the position operators in a row, Q0, Q1, Q2. And then once we're done with those, we're going to put all the momentum operators in a row. Sometimes people will be like Q0, P0, Q1, P1, and kind of like interleave them. That's good too, but we're not going to do that here. Okay. So the first moment is a vector of the expectation values of those guys. In other words, the expectation values are the means of all of the position and momentum operators. So, you know, like I'm just going to index this vector of operators, you know, like VI. And so, you know, the first moment is this vector here. Where, you know, I've just like suppressed the, you know, this is like the expectation value on some state. The second moment corresponds to the so-called covariance matrix. So to form that, we iterate over V twice and form a matrix whose elements are given by these expectation values. In other words, you know, we take VI, VJ plus VI, and take the expectation of that value of that minus 2 times the expectation value of VI times the expectation value of VJ. And remember, like VI or VJ or whatever, they could be, you know, a position or a momentum operator. You know, we just notated it so we don't have to worry about that. So, you know, just explicitly, like you could write out this matrix like this. So, you know, these give, you know, it's like, these are all the ones where like, yeah, V0, you know, and then it's like V0, V1, V0, V2, and then V1, V0, et cetera, et cetera, et cetera. So that's the covariance matrix. So as I say,
Matt, can you tell us what it represents physically? I see the mathematical definition, but physically, what does it mean?
Yeah, you know, like Yeah, I mean, you can think about it like it sort of measures how the different modes like relate to each other. Okay. I could say more about it, but like let me go on a little bit more, and then we'll maybe some certain things will become clear.
Okay.
Um. So oh, just got a buzz. Oh, sorry, someone wants to come in to the meeting. Hello. Okay. So, so Gaussian states are fully characterized by their first two moments. So, in other words, if I have, a vector in a matrix representing, the first and second moments, I can get a Gaussian state. If I have a Gaussian state, I could like get these first two moments, and they fully characterize each other. And so, if you think about it, you don't even ever have to work with the state vector or anything. Like you could just work with, if all you care about is Gaussian states, the first and the second moments. That's all you need to do. Furthermore, like if you have a bunch of oscillators, as we do in this case, you can extract like the partial states for each oscillator by just considering those elements that involve a particular oscillator's P's and Q's. In other words, we just wanted to focus on like take the partial trace, basically on like the first, look at the first oscillator, we would just take just the part of the first moment vector that just, involves, Q and P on the first guy. And then we just would take the chunk of the covariance matrix that involves Q's and P's on this particular, the 0th oscillator. And then just culminating here, this final section here about the, this sort of basic Wigner stuff is that from the first and second moments, you can easily just like write down the Wigner quasi-probability distribution. So if we define like a vector of variables, here's our Q's, here's our P's, we can just like construct this. So it's like 1 over little normalization thing, square root of the determinant of the second moment. And then it's like e to the, and then you have here basically, the variables minus the first moment vector. Here you have the variables minus the first moment vector. This is a transpose of that. You have the inverse of the second moment matrix, the covariance matrix in the middle. And if you look at that, you're like, that's just ripe for some Gaussian integration. In fact, like that's basically the general form of like something that you can easily do Gaussian integration over, okay? And in fact, like this is like kind of one reason, as I'm saying, like the quasi-probability distributions are useful because for Gaussian states, like this just takes this like very beautiful, simple form. So thinking about, okay, more about Gaussian states. So, Gaussian states include the vacuum state, position, momentum eigenstates, coherent states, which are like displaced vacuum states, squeeze states, displaced squeeze states, okay. Corresponding to the states, we have like Gaussian operations, like which preserve Gaussian states. So for example, displacement operators, squeezing operators, and in fact, evolution by the oscillator Hamiltonian itself. And for multi-mode states, you can have your 2-mode squeezing operator, your beam splitter. And in general, if an operator can be written as an expression quadratic in creation and annihilation operators, it's Gaussian. So, we've talked about some of these before, if you're just curious, like in terms of operators that act on wave functions, this is what they look like. So like this is like the displacement operator. It's parameterized by some complex number z. And you get this squeezing operator. Let's not dwell too much on these. It's just sort of for completeness' sake. Instead, let's like look at these things, okay? So what we have here, I'll show you the code in a second. Just like a little thing to play around with like exploring Gaussian states for a single mode What you have here are here's the position distribution and here's the momentum distribution. And we start off in the vacuum state. And indeed, you see the vacuum state in both position and momentum symmetrically. It's just a nice little Gaussian. Now we can use these sliders here to perform like the classic Gaussian operations on this single mode. So, you know, we can explore doing position displacement. What happens? Indeed, the displacement operator is well named because it just displaces the, you know, the little probability guy for position, you know, just like away from the origin. That's why it's called a displaced, you know, vacuum state. And, you know, hearkening back to stuff we talked about weeks ago, these are the coherent states. Another way of saying it is like, if you look at like all of the displaced vacuum states, those are the coherent states. And, you know, we like sort of went into the fact that they form an over-complete basis for oscillator states. You know, this was back, you know, a couple months ago. Anyway, so, you know, you can displace in position, you can displace in momentum. That's cool. Squeezing, like what is squeezing? Squeezing's like you kind of pinch it in position and it gets fatter in momentum. Or go the other way, it's like you pinch it in momentum and it gets fatter in position. So it's like squeezing, you know, kind of involves this trade-off, ultimately due to the Heisenberg uncertainty principle between position and momentum, you get these squeezing states. And then, you know, rotation, this is just parameterizing the harmonic oscillator Hamiltonian. So, you know, you can think about this as just like, this is just like evolving under the oscillator Hamiltonian, and, you know, these guys are just gonna like oscillate back and forth, although you see they also kind of pulsate, you know, based on the extent to which they're squeezed. So, I mean, just to give it a better sense of that, let's just, you know, like displace this guy over here, and then like, let's look at how it evolves. And, you know, both in position momentum, it's except at like some offset from each other, they're just oscillating back and forth like, you know, harmonic oscillator do. On the other hand, you know, if we squeeze them a bit, then the oscillator Hamiltonian, yeah, they're going back and forth, but they also kind of like, you know, kind of unsqueeze and squeeze themselves. Like they kind of like trade off, like who's squeezed, you know, position or momentum. So, okay, so that's just like to give like a general intuition for like, we're talking about Gaussian states just for a single oscillator mode. You know, what are we talking about? And like, yeah, we're just talking about like, yeah, they look like normal distributions, but like they can be displaced from the origin. They can be, you know, squeezed, or they can be sort of like, you know, spread out. I mean, you can think about like, you know, like check it, like let's squeeze this guy. Like, look what's happening. We're like really pinching it in position, and, you know, it's getting super spread in momentum. Now imagine doing that to infinity, okay? Then like at infinity, this position guy is gonna be like infinitely squeezed. It's gonna be just like a spike. And then like in momentum, it's gonna be like infinitely spread out. And you're like, oh my God, that's just a position eigenstate. That's another way of thinking about what a position eigenstate is. It's an infinitely squeezed state. Similarly, we can like squeeze it in, you know, a shit ton. Oh, so if you squeeze it too much, you know, the thing craps out. It's just like the visualizing thing, because you know, you only sample it at certain discrete points.
Matt, what is rotation again? What is that doing?
Yeah, so rotation is just the normal oscillator Hamiltonian. So, you know, you can think of it like kind of like a phase rotation. So here,
it's a phase. Okay.
Yeah. So it's just, you know, this is just like the number operator, you know, basically. I guess technically, you know.
So it's a phase change. It's a phase change. What it is. Yeah.
Yeah. So you have this little theta.
Rotating the QP plane, isn't it?
Sorry, say that again?
It is a rotation in the QP plane.
Precisely. Yeah, exactly. That's right. Yeah, so not like a 3D rotation, but yes, like a rotation in this phase plane. So, all this code does basically is prepare in the vacuum state. It's got these sliders and just, depending on the sliders, we do a squeezed gate parameterized by the slider values for squeeze. We do a displacement gate parameterized by the values,
Could you repeat the rotation thing just to see what it looks like?
Yeah, well, on what kind of state do you want it to be?
Well,
so,
just change it. I mean, let's see what it looks like by changing it.
So like on the vacuum, nothing happens, right? So it just like sits there.
Oh. So where does it come in?
Variant. Well, because remember, the vacuum state's an energy eigenstate. And so it's an eigenvector of this rotation operator. So it's not going to change. On the other hand, if we, let's like displace this dude a little bit, then they just go back and forth. In fact, yes, since we're interested in this, let me open up.
See, I'm trying to relate this to something that I can identify with instead of.
So it was kind of slow in the notebook, but here, if I run it standalone, you see it's like much snappier.
Instead of P and Q, we can consider this in the frequency and time domains. So what would a rotation be? A rotation would be a phase difference.
So you see under the rotation, this Q is just sort of, we've basically taken this guy and just moved it to the right a little bit. And if you recall, we talked about this when we were discussing coherent states. The expectation value for position of this guy, like literally just mimics that of a classical harmonic oscillator. So we just like displace it a bit, and now it's just oscillating back and forth. It gets a little bit more fun when we, squeeze them a little bit. And then as it evolves, they kind of like, trade off, like who's squeezed, position, momentum, like as they're oscillating back and forth. Bing, 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 bing. Too fun. Just like watching. Okay. So let's think about, now you might be like, all right, this is like, okay, something might be brewing in the back of your head. You're like, all right, so Gaussian states can be fully characterized by their first and second moments. Now, we could represent states like, using a state vector. Could represent states using a quasi-probability distribution. We might be like, well, I mean, if Gaussian states are just characterized by their first and second moments, like, why not just stick with those? What do we need state vectors or quasi-probability distributions or whatever? Okay, can we just get away with just that? And you can, yes, of course. But like, how are you going to represent stuff on those operators, like on those first and second moments, right? Like, how are you going to represent, evolution, different operators, different kinds of measurements and stuff? And so there's a way to do it. And it's going to take us back to a topic which we've already discussed, when we were discussing the Bogoliubov transformations, or, that stuff having to do with, curved spacetime or whatever. We talked about symplectic transformations. And that's, okay, yeah, this is like this, what, about to talk about is like the revenge of the symplectic transformations. Like that's the answer to this question, okay? So.
Matthew, can you remind us what the symplectic transformation is?
Yes, so that's what I'm about to do. Okay, so a symplectic transformation acts on a space of even dimensions. And you can think about it like it preserves the special commutation relationships between position and momentum. So, concretely, what that means is a symplectic matrix preserves the symplectic form, which in this case, we can write it as omega, and it's going to be this little guy. So, this is a matrix. This is an n by n submatrix of zeros. This is like a, n by n identity, and so forth. So this overall is a 2n by 2n dimensional matrix. And when we say that a symplectic matrix preserves the symplectic form, what we mean is if we act with the symplectic matrix and its transpose on either side of omega here, it just gives us omega back. And so, in general, like these are often known as like, in a sort of a classical mechanics context, and known as like canonical transformations. The idea is that they're transformations that, preserve the fact that like you have a bunch of positions in momenta. Like in other words, you define your system and there's these variables that are conjugate to each other. Got a bunch of positions, got a bunch of momenta, whatever they may be, in your context. And then you do a transformation on all those guys. And the idea is like, you get some new positions and some new momenta. And they're like, have that special relationship to each other, but they're just different ones. And they're like built out of the old ones, but they still have that property of being, positions and momenta. So that's, that's what we're talking about here. So a general finite linear, there's other kinds, more fancier kinds of symplectic transformations. Finite linear symplectic transformation consists of a symplectic matrix and a displacement vector D, and it transforms the first and second moments of a state like this. Basically, the first moment transforms like you multiply, you act with it with the symplectic matrix and you add the displacement vector. And the second moments transform like that. You just sort of multiply them. S on the one side, transpose of S on the other side.
Matt, would you say is a symplectic transformation the same as a diffeomorphism?
I would not say that exactly, no.
It is a special case of a diffeomorphism.
What is that motion? We can't hear you.
It is a special case of a diffeomorphism.
But it's essentially it's the conservation of the Liouville whatever.
Yeah, maybe. That's a good question. I hesitate to call it, because I guess I hesitate to call it diffeomorphism in the sense that, again, I'm not an expert on this topic in general of like symplectic transformations, but in general, it's like symplectic spaces sort of, you're kind of, it's a geometry based on like area as opposed to like points. And so I don't know if like the idea of a diffeomorphism is like exactly as like relevant.
No, but like Moshe said, it's a special case, but I think it has to do with the conservation of the Liouville transform or whatever you call it.
Maybe that's possible. So, up here, I gave the representation of like these operators on wave functions. Okay, so they're kind of built out of creation and annihilation operators, whatever. So now, like, let's represent those same things as symplectic transformations. So, the displacement operator is just really simple. The symplectic matrix is just like the identity. And given Z, and again, this is just acting on a single mode, you just form this displacement vector, which is like the real part of Z and the imaginary part of Z, and you add it to the first moments, and that's it, easy. The symplectic matrix corresponding to a single mode squeezing operator is just this guy. It's parameterized by some complex number, R to the E I theta. And, you got some hyperbolic sines, cosines, whatever. When theta is 0, this just like amounts to this. And so, you would use this matrix, act with it on the left and on the right with the transpose on your second moment matrix. that should be a little typo there. I've been trying to be consistent, putting these 2s everywhere. And, you know, you can this is just, you know, for like, where we're going to go is I'm eventually going to show you like how you can derive these things. But, you know, just like for now, you know, we can represent the oscillator Hamiltonian, you know, in terms of these sines and cosines here, get that symplectic matrix. Here's the 2-mode squeezing operator. And, you know, if you have to act on like more than one mode or something, like you have a bunch of modes and you want to like act with one of these guys just on a particular mode, you know, you just take the 2n by 2n identity and just, you know, figure out like, okay, which are the components corresponding to the P's and Q's of the you know, the oscillator mode you care about, and just, you know, pop in the components of this guy or whatever. So,
Right, Matthew,
yeah.
the way you define symplectic transformation is that they preserve the specific matrix with identity minus identity along the cross diagonal.
Mm-hmm.
What's so special? Why is this especially relevant to have transformations that preserve omega? Why do we care about it?
Yeah, so I should have written this out. But if so, you know, if you take you know, your vector of position and momentum operators, and you multiply it by this guy, it's essentially going to construct the commutator between positions and momenta. And so essentially what this, if you're preserving this matrix, you're preserving the commutation relationship between Q and P. I should have written it out. But that is the effect of it. So basically, you know, you have your famous Heisenberg commutation relationship, and you know, if you act with one of these guys, you know, you'll get a bunch of other matrices, but they'll be arranged into P's and Q's, and the commutator is, you know, whatever, I or one.
Okay, I get you. Thanks,
Yeah.
Matthew. Thank you.
Yeah, when I revise this, I'll expand that section. I'll like work, you know, I'll make that visually obvious. So, all right. So this, okay, so I just, you know, before when we visualize stuff, I use strawberry fields. Here I sort of like do it by hand just for sake of argument. So I won't, you know, explain every part of this code, but, you know, basically, you know, this is a function that, given a single mode operator, symplectic operator, you know, it upgrades it to act on the ith of n modes, right? This code here like extracts the partial state of like the ith of n modes. Here, given some state, this calculates the first and second moments. You know, you just see it's just taken the expectation value. V is this vector of, you know, positions and momenta. You know, this is just sort of a translation to code for what we saw before. Here, you know, these just construct those matrices we just saw, the symplectic matrices for, you know, squeezing and rotation and 2-mode squeezing, whatever. Here, this applies a symplectic transformation. You see it just take S on the first moment vector plus the displacement, you know, et cetera, et cetera, et cetera. Here, given first and second moments, this constructs the Wigner function, like by hand, in terms of SymPy, you know, to handle the algebra. So here's that expression that we had for the for a Gaussian quasi-probability Gaussian function, you know, where we had an exponential of the variable, you know, vector transposed on the you know, et cetera, et cetera. That's just this thing from up here. Where was it? beep, beep, beep. That's just this translated into code. And basically, then this sort of like plots the different modes, and you can see both the Wigner distribution as well as the positions and momenta. So like, let's just look at it. So we'll just start off in the Gaussian. Oh, typo. That's fine. That's fine. Fixed it up. Okay. So here we start off with two modes. Why not? Both in the vacuum state. So we can see, here's the vector of first moments. Here's the vector of the first moment vector, second moment vector. You see they have this very simple form when you just have the vacuum state of two oscillators. These are all 0, which makes sense. I mean, nothing's been displaced at all. And the second moment matrix is just the identity. We just check that, integrating over both positions and momenta gives us 1, so probability is preserved. And you see here's like the first mode. It's just that, vacuum state Gaussian that we saw before. And here's, the probability distribution for momentum. Here's the one for position. And then here's, the second mode also in a vacuum state. But, we can do stuff. So like, let's, displace the first oscillator by some random amount. So you see here, this is the Q component of the first oscillator. Here's the P component for the first oscillator. And you see displacing it hasn't changed the covariance matrix at all. Let's just change this first moment vector. We see that, hey, look, yes, we displaced the Gaussian like in this phase space plane. And, we've just sort of moved Q and P a little bit to the side. Okay, displacement makes sense. Instead of displacing it, let's do a squeeze on the first mode. Here, under the squeezing operator, first moment vector doesn't change, and we get this sort of squeezification here on the second moments. And you see that these guys have been, well, that's not very, let's do it again. I mean, that's not very squeezed at all. Maybe this will be a little bit more squeezed. Yeah, a little squeezed. Let's do, for example, let's just do all these. Okay, so we're gonna displace the first mode, squeeze it, rotate it, and then do a 2-mode squeezing operation on the first and second oscillator. So then we end up with like, these moments. We see that we end up with this guy kind of squished and displaced and rotated, and this guy's kind of squished and displaced and rotated. And that's what it's all about, basically. Okay. I just wanted to, if you're interested in doing this by hand, I mean, it's like, instead of relying on Strawberry Field's function, you can, just use SymPy or something and represent your quasi-probability distribution, and then, do your integration over momentum or position yourself. Okay. So let's not dwell too much on that. All right, so now here we're coming into we're getting closer and closer to the conclusion. And if you know anything about me, the conclusion is probably going to involve yet another representation of spin. And so that's where we're going. But to get there, and this shouldn't take, longer than about 10 or 15 minutes. In order to get there, like, we're going to talk about how, like, to go from, suppose we have oh wait, sorry, something in the chat that I didn't notice from before. Oh, okay. Oh no, Krishna, I never admitted him. Damn. I gotta, sorry. Sometimes these windows, these little Zoom windows get lost in the mix. Anyway, so I mentioned that like a Gaussian operation can be thought of as like a unitary matrix, right? Which you get by exponentiating Hermitian matrix, but specifically where the H here is quadratic in the creation and annihilation operators. So, you know, the idea of a Gaussian operation, something that's quadratic in the creation and annihilation operators, these are the same concept, okay? So you might wonder, like, suppose we had like a Hamiltonian that was like quadratic or whatever. How would we find the corresponding symplectic transformation? So here's how you do it. It's actually really easy. So before we defined a vector of, you know, position operators and momentum operators. Now let's sort of do something analogous and define a vector of operators, which consists of like the creation operators, sorry, the annihilation operators, and then the creation operators. So this is a 2n dimensional vector of operators, the n annihilators and the n creation operators for the different modes. And then this Hamiltonian, like a Gaussian Hamiltonian, can be written in this compact form, where H is just like some Hermitian matrix, and there, let's say bold H is a 2n by 2n Hermitian matrix. Little bold h is a 2n complex column vector, and we've sort of taken a sort of, we've like sort of, so, okay, so this is just from the definition of it being built out of like a quadratic expression of creation and annihilation operators. In other words, this is like a, you know, a row vector of your creation and annihilation operators. This is a column vector, okay? And then you have this 2n by 2n Hermitian matrix. So, you know, this just like is parameterizing basically some polynomial in your creation and annihilation operators where the components are coming from this Hermitian matrix. And because the way that we've set it up, the, you know, the terms involving only a creation operator or an annihilator come from this, right? So H is just some complex numbers. And so this is the vector of annihilators and creators. And so this just gives you your linear terms. And then this guy gives you your, you know, quadratic terms, because like each term in this is basically going to end up being like a complex number times a creation operator, like times an annihilation operator, or an annihilation operator times a creation operator.
Matthew, I'm a little bit confused here. The first term that you have is basically a scalar. The second one is a vector. How can you add a scalar to a vector?
So, so in fact, so chi here is a vector of operators.
Okay, I see. Okay. I take it back. Two scalars, no problem.
Yeah, totally. So, you know, effectively, this is just multiplying each operator in this vector by one of these numbers and adding them up.
Right.
And furthermore, we can take, you know, bold H here. It's a 2n by 2n Hermitian matrix, and we can actually sort of like kind of think about its block structure as like A here is itself an n by n Hermitian matrix, and B is a symmetric matrix. We're gonna come back to that in a second. So here is just some code that generates, you know, like a random, you know, quadratic, you know, Gaussian Hermitian matrix. All right. Now this is like less trivial in a way. It turns out that evolving all of your creation and annihilation operators by a Gaussian unitary is equivalent to this affine transformation. In other words, here we have H is our like Gaussian Hermitian operator. E to the I H is our Gaussian unitary. So this is just evolving each creation or annihilation operator in that vector chi by your Gaussian unitary, acts on both sides. So this is just like going through and like evolving each of the creation and annihilation operators by this Gaussian unitary. And it turns out that's just the same as taking this matrix S and just like acting with it on chi, and then adding this little s, where S, bold S, is a complex symplectic matrix, which you can derive from the Hamiltonian as just e to the negative I omega c h, where omega c is the complex symplectic form, which is this. And so this is like, if you think about it, like the real symplectic form was preserving the relationship between positions and momenta. The complex symplectic form is preserving the relationship between creation and annihilation operators. So it's preserving their commutation relations. And we can get basically this complex displacement vector, little s here, by just doing this little thing. Just take, s minus this identity and then h inverse and whatever, technical detail, whatever. Okay, so here's the code that does it. This basically generates a random Gaussian, whatever, Hermitian matrix. It's quadratic in creation and annihilation. And then this just implements this little expression here to derive a complex symplectic matrix. So this is just this translated into code. And so this is like basically a guy that acts on a vector of creation and annihilation operators. So now the final step is to convert that complex symplectic matrix into a real symplectic matrix that acts on the vector of positions and momenta, okay? And so what we're gonna do is basically this matrix L here, I'm defining it as, here's a n by n identity block, and it's got this. So if we take our vector of creation annihilation operators and multiply it by L, we're gonna get our vector of positions and momenta. Why? It basically just comes from the definition of Q and P in terms of creation and annihilation. So, the position operator is just, annihilation plus creation. Momentum is just negative I times annihilator minus creator. And so sort of that's where this negative I, et cetera, is coming from. Again, maybe when I revise this, I will write this out like more explicitly, but essentially, what this matrix is doing is just applying this rule as a linear transformation to like all of the modes. In other words, given a vector of creation and annihilation operators, it just takes all these linear combinations to give you instead a vector of position and momentum operators. So then, given a complex symplectic matrix that acts on a vector of creation and annihilation operators, we can get a real symplectic matrix that acts on a vector of positions and momenta. And it's just this, you just sort of conjugate it with L, and you can get little r, the real displacement vector, by just acting on S with L. And actually this came up in one of the papers, you can also equivalently, express this by dividing up the complex symplectic matrix into these blocks and taking some real and imaginary parts. And then finally, the key is that so far we've been able to like sort of come up with this either complex or real symplectic transformation that acts on either the creation annihilation operators or the position momentum operators. The key then is that, our Gaussian states can be fully characterized in terms of their first and second moments, and then these real symplectic transformations just act on those guys. So we use them not to actually like act on the operators, but instead to act on the first and second moment vectors. And then it just like implements the Gaussian unitary. So that's how you go from like taking a Gaussian unitary to representing it as, you know, a real symplectic matrix that acts on the first and second moment vectors. And so, you know, this just sort of completes it. So we sort of generate a random quadratic Hamiltonian, get the complex symplectic matrix, get the real symplectic matrix, and in fact, I calculate it, you know, using these two different methods I mentioned here, and indeed, it's, you know, you get the right answer. Okay, so now suppose we're working in a second quantization context. All right, so like our first quantized system has n basis states, so we introduced n bosonic oscillators to keep track of the number of particles in those states. And so what that means is that we could like upgrade a first quantized operator to a second quantized operator by just taking the first quantized guy and kind of wedging a vector of creation operators and a vector of annihilation operators on either side. Now you look at that and you're like, oh shit, you know, that's just clearly big O is going to be like no more than quadratic in the creation and annihilation operators. Basically, for each term of O, for each component of O, we have basically a, you know, a creator times an annihilator times a complex number, and then like add it all up. So like any second quantized operator is, you know, going to be able to be represented as a symplectic transformation. And so, you know, we can actually just take little o here, the first quantized O, and pop it in for A in this expression for the Hamiltonian from before. You know, the idea is that like here, or previously, this is a vector of like annihilators, all the annihilators and all the creators. And here, you know, this is just a vector of the creators, and it's just a vector of the annihilators. So we just have A here being like the first block, O becomes A, the B's are just 0, and then that's just, you know, O conjugate. Basically, like, we don't need those other terms, okay? And so here, now we're really coming sort of to the finale here. So here's a little function that, given some first quantized operator, turns it into a symplectic transformation on our Gaussian oscillators. We can indeed like apply this to, you know, Pauli X, Pauli Y, and Pauli Z. Remember, we've been playing around for like quite a while now with this representation of spin, where we introduce two harmonic oscillators. One to keep track of the number of Z up states and one to keep track of the number of Z down states. I won't go into like the full review of that whole theory because we have talked about it quite a lot. But, you know, this is the sort of famous sort of second quantization or Schwinger, you know, oscillator picture of spin. Ultimately, what it means is that we can sort of represent the Pauli matrices as, you know, real symplectic matrices that act on two oscillator modes. So here they are. Here's a function that what it does is, given a state, a strawberry field state, calculates the expectation value of X, Y, and Z. So basically, if you interpret this as sort of wedged between, you know, your vector of position and momentum operators, this is basically going to correspond to a second order polynomial in the positions and momenta. And then you can sort of calculate the expectation value of this operator by individually calculating, you know, the expectation values of the positions and momenta and their combinations, and then adding it all up, weighted by, you know, whatever the coefficient in the polynomial is. That's a little bit, you know, we don't have to worry about it in a sense, because strawberry fields gives us this great little function here, polyquad expectation. We just give it our matrix. Here's some code that converts from Cartesian coordinates to spherical coordinates. And here's some code that, given an XYZ location on the sphere, constructs a series of rotations, 2 rotations, as Gaussian transformations on the oscillators that take you from the Z up state to the desired state that you've chosen. In other words, this will give you 2 Gaussian transformations that prepare an arbitrary qubit state built out of 2 oscillator modes. So you start off in the up state, and then you say, oh, I want it to be pointed in this direction. And so this is gonna rotate it. So given the representation of that Cartesian point in spherical coordinates, there's many ways to do this, but here we represent it as a combination of X rotation and a Z rotation, by this amount. And Strawberry Fields provides this little guy, Gaussian transform, that allows us to wrap a real symplectic matrix and then apply it to our oscillator modes. So, okay, so here's where we've been headed. What this code does is well, let's just look at it. So here we have a representation of spin on 2 harmonic oscillators entirely using Gaussian states. So here are the Wigner quasi-probability distributions for our 2 modes. And here's the Bloch sphere of our qubit. And what I asked it to do was to start in the Z up position and then to rotate around the Y axis. And we can watch as the qubits, rotating, what's going on with the quasi-probability distributions. And so we can watch it. So, just to briefly summarize how it works, we choose which rotation we want to do, what initial state we want. Specifically, we use Strawberry Fields' Gaussian backend because it's efficient and we're just working with Gaussian states. Here, so we're gonna make a movie, so we gotta repeat everything as many frames as we want in the movie. So we create the Gaussian transformation corresponding to the rotation by a certain number of degrees, depending on what frame of the movie we're in. Basically, given the initial state, this is that function that generates the Gaussian transformations that take us to the desired qubit state. And then for each frame of the movie, we create a Strawberry Fields program on 2 oscillators, start off both oscillators in the vacuum state, prepare the Z plus state by squeezing the first mode. So that's essentially the Z up state. And then apply the 2 Gaussian transformations that then rotate the qubit from the starting state to the state that we actually want to start from. And then we perform the Gaussian transformation of the rotation for this frame. And then we get the quasi-probability distributions and we update our plot. Now I have a standalone version of this so that, kind of looks prettier in the sense that it's more, it's less choppy. So let's just look at those. Okay. So this is the fun part. And in fact, I'm gonna loop them. Loop. Loop. And loop. Let's make them all, let's fit them all on screen at the same time. Okay. So this is, our qubit in each case starts in the Z plus state. To the left here, we're doing an X rotation. In the middle here, we're doing a Y rotation. And over here, we're doing a Z rotation. So, just considering the Z rotation first, we started in the Z up state. So obviously that doesn't do anything to the qubit, but we see that, we prepare the Z plus state by squeezing the first oscillator mode, and the Z rotation effectively, boils down to actually just the harmonic oscillator Hamiltonian, which, as we were pointing out earlier, is just a phase space rotation. Meanwhile, we're looking at like the X, rotation, and we can see that it's sort of, we're sort of, bouncing along, but sort of like trading off, like which one is squeezed and like which one isn't squeezed, right? It's like now it's squeezed, now it's not, now it's squeezed, this one's not, that's squeezed, okay, you see. So, it's sort of kind of addictive to watch these little guys just bouncing along. Then I got, 3 more ones. So those, were just ones where you like started out, in the Z plus state. We can do one where, you just start off some like random location, which just will give you like a better sense of, what these kind of things look like. Loop, loop, loop. So again, this one's doing an X rotation, this one's doing a Y rotation, this one's doing a Z rotation. And in each one has started out in a different random state. And so you can see, like they're kind of interesting. Like this one is like the Z rotation, they're clearly like both kind of like rotating around, but this one seems to be going at like a faster rate. I'm just making sort of qualitative considerations here, as I look at them. So that's useful. You're like, hey, I got a photonic quantum computer. Now, there's all sorts of fancy ways that people have come up with to represent, say, like qubits using oscillator modes. In fact, far more sophisticated ways than this. But, just as an example, to get the hang of, okay, you want to sort of represent spin in a second quantized picture. So you're like building it out of oscillator modes, but hey, it's a second quantized operator. It's going to be, no more than quadratic in the creation annihilation operators. So we could just represent that with a symplectic transformation. So how do you construct that symplectic transformation? And then maybe you stick to working, with Gaussian states. So then, you can describe the whole thing very efficiently with just a vector of first moments and a covariance matrix of second moments, and use your symplectic transformation to transform those, and do all of this without even ever involving a state vector. It's kind of sweet, and it's like super efficient. So if you're interested, there's a link here to like the standalone version of like this code, which is fun. You can generate these movies. Got some, bibliography here, some nice papers that go into this stuff. And then, the final thing I'll just say is, this is really for the Brooklyn Quantum regulars here. You may recall, our meeting from a couple weeks ago where, we were talking about this sort of ATIA construction meets the Barry Robbins spin statistics theorem thing, where we have like endpoints in 3D and each one has a spin. And then, we do this funny thing with the calculation, with the constellations to generate a transformation that like swaps the spins if they swap locations. If you know what I'm talking about, you know what I'm talking about. It may occur to you that, hey, those exchange rotations were just basically, Pauli rotations, like spin rotations, like across different spins, which were represented as oscillators. So here I have, written out like another version of this that uses Strawberry Field's Gaussian backend to do this in a quantum way that's very efficient. So, for those who are not familiar with this, what you should be looking for here is, as I take this spin, like, see this guy's pointed at this little green spot. when I move this guy and swap locations with him, now this guy's pointed at that green spot. In other words, as these little spins swap location in position, they also swap their spins. And so, okay, that's a little bit annoying. This is like a model of, you know, permutation, symmetry. Anyway, I just, for those who recall this construction, you may remember me complaining about how I couldn't do it efficiently and it was bothering me. Well, turns out Gaussian quantum mechanics was the answer. Anyway, thank you for listening. Any questions, concerns?
Yeah, I was hoping you could follow up with more on Wigner's, what is it now? Wigner's, all these polysyllabic words get to me. Wigner's quasi-probability distribution.
Mm-hmm.
And, you know, for those of us who are really more into quantum mechanics, the practical aspects of quantum mechanics, if you could follow up next time with what the advantages are of Wigner's methodology. And you also, you know, apparently you're somewhat familiar with Glauber's work, which, you know, I'd be interested in particular because my training is electrical engineering.
Yeah, so
Signal analysis. If you could get into that.
Yeah, so in a way we've already done that. Like the way of thinking about it is that the Glaubner coherent states consists of all of the displaced vacuum states. So that's what they are.
Could you relate that to laser technology? Coherent states and, you know, laser technology? I mean, I know this is far afield from what you're interested in.
No, I mean, it's the same. No, it's definitely the same idea. And again, like they're building these, you know, these kinds of quantum computers out of light. So again,
right.
You know, when it comes to practicality, like all this stuff is you know, used every day by people who work on these photonic quantum computers. So you know, the oscillator coherent states, which consists of these displaced vacuum states. So you imagine you have vacuum state, and then you imagine like all the different ways you can displace it. And again, you can displace it in position and momentum. So then, you know, all of the different coherent states correspond to different locations on this plane, this position momentum plane. And so for every point on that plane, you have a coherent state, which consists of the vacuum state that's been displaced. And the relationship to the sort of, you know, so there's a thing you can do, like that's sort of analogous to a Fourier transform, although it's more analogous to a wavelet transform, is to take, it turns out you can take any oscillator state, Gaussian, whatever, it doesn't matter. And if you take its inner product with all of those coherent states, then that forms a complete representation of that state. So we talked about this like a couple weeks ago. So that's like it's a form like an overcomplete basis. In other words, it's like you know, it's not like a orthogonal basis or anything. But, you know, you can kind of sort of construct a coherent state wave function, which is like given a state and a complex number that parameterizes a point on the complex plane, which corresponds to a certain coherent state, which is just the vacuum displaced to that point. You take that amplitude, that function provides a complete representation of the state. And so, you know, I don't know that much about wavelet transforms, but like that's similar to the idea, like you take one basic wavelet and then you know, sort of displace it in a bunch of places and then sort of like check the overlap with your, you know, given function. And then that forms a complete representation of the function. So, yeah, like, you know, so that's what's going on there.
But I was wondering if we could in the future relate it to what, current technology, what's going on, or even, recent technology.
Right. Well, I should have emphasized more about like this Strawberry Fields thing then. So, you know, the context here is that Xanadu is this Toronto-based quantum computing company, and they are building, you know, photonic-based quantum computers. So
Right.
you can you know, request access to their beta or whatever. So then Strawberry Fields is their, look, they got really fucking cool Wigner quasi-probability animations. Look at that thing go. Let's like watch it again. I want to see it again. Whoa, look at that. So yeah, so like it's worth, you know, going through their documentation here. And, you know, again, like unlike a qubit-based quantum computer, this is all sort of oscillator mode based, right? So they have these primitives, you know, instead of the primitives being like X rotation, Y rotation, C naught, like whatever, they're like displacement gate, you know, position displacement gate, you know, quadratic phase gate, you know, whatever, beam splitter gate, all this stuff. And, you know, you can like get, you know, prepare a coherent state, prepare, you know, a squeeze state. And, you know, it's all based around, like if in a qubit-based quantum computer, it's all about like at the end of the day, measuring the spin in the Z direction. Here, you know, it's all about like either measuring the number of photons in a mode or measuring the, you know, X or the, you know, the position or measuring like the momentum. And you sort of like build your other operators, you know, out of those. And then, you know, they themselves provide a way of, you know, dealing with, you know, Gaussian transformations, like I'm saying. And in fact, like, you know, if you look at, say, a state, you know, Gaussian backend state, and you look at the functions that they provide, you know, like immediately they give you, where is it? Oh no, this is, sorry, that's the wrong one. State, base Gaussian state. Yeah, so look, you know, you can see right here that their Gaussian quantum mechanics simulator, like the way that they even represent the state is in terms of the vector of means, that's the first moment, and the covariance matrix. And so, you know, given one of these states, you can like ask it like, oh, you know, what's the covariance matrix? What's the means? So like, that's actually how they're representing it internally, which as I say, makes it like very efficient. And actually I will mention, you know, if you look here on their website, you know, this, they have a great thing, you know, where it's like, unlike a lot of these quantum computing like documentation things, like they actually kind of go into the theory in a nice way. So, you know, they go into the difference between, you know, qubits and Q modes. You know, here's like the list of, like I'm saying, these are all the different kinds of, you know, Gaussian states. You know, these.
You know, Matt, Matt, you're probably familiar with Quantum Appaloosa. Do you look at any of their daily?
You know, I have to say, you know, Terrell, that's Terrell's thing, right?
Right, and he always signs up for this meetup and for the New York meetup, and he never shows up. That's right. It's Terrell France. He's at Harrisburg.
Yeah, very
So
thankful.
how come I haven't heard of Xanadu? I hear of everything, Qiskit and all this other stuff. I haven't even heard of Xanadu. and Strawberry Fields. Why doesn't he have some of that stuff?
I don't know. I mean, to me, like they're kind of like in my world, like they're kind of blowing up, I would say, in the sense that, you know, everyone's really into their other, you may have noticed everything about them is named after a Beatles song. So Strawberry Fields, their other library is called Penny Lane. They got their quantum, like sort of assembly language is called Blackbird. One of their back end libraries is called like The Walrus, as in I am the walrus. And that's just cute. But Penny Lane is a quantum machine learning algorithm, library that everyone's real excited about. So, you know, and it's cool. So like Strawberry Fields is sort of like for interfacing with photonic-based quantum computers, of which they have one, as I say, like that's in beta or whatever you're especially.
Is there a political reason why this has not been publicized on Quantum Appalooza? You know, Terrell seems to publicize, you know, the IBM and the Google stuff. But a lot of the, I haven't, like I said, I haven't heard of Xanadu until now.
I don't know.
I don't know. This must be political. They're probably trying to keep competitors
maybe. I don't know.
out. I don't know. And Terrell's not here, so we can't confront him with it. It's Jamie, really? Oh, I guess I'm wrong. Jamie says it's on there. Okay, I guess I missed it.
So I mean, one thing I'll say is that so whereas Strawberry Fields is like all about interfacing with the photonic stuff, Penny Lane, you know, actually can operate with photon-based quantum computers, qubit-based ones, you know, different kinds of classical simulators, like automatically works with like, you know, TensorFlow and other stuff. And, you know, is all about like kind of creating quantum functions that are like differentiable. So you can do like, you know, machine learning on them. And, you know, they have just great documentation, really cool stuff involving, you know, quantum chemistry, like taking, you know, basically like a water molecule and you know, kind of like figuring out how to represent it in terms of, you know, qubits and stuff and like doing training on it.
So this is more photonics than it is superconducting quantum computers.
Well, so that's what I'm saying. So
which
Penny
is what
Lane,
IBM and Google are working on.
So Penny
there we
Lane
go. Okay.
works with all of it. Like, so that's what I'm saying. So
yeah.
That's like their general quantum machine learning framework. So like they have like built-in plugins for working with like IBM stuff or Getty stuff, like whoever you like. But then you know, they themselves as a company are developing a photon-based quantum computer that is in beta, actually. So people are using it, like not me, but I apply, you know, I requested it. And so, you know, Strawberry Fields is the, you know, interface for that. So, you know, we were using it, you know, just the simulator part. But, you know, as you can see here, it's all set up for like, once you do get your account to like run all the same stuff on, you know, whatever. On the real thing, the X8. Yeah. Yeah, I mean, they have, I just have to say, you know, they really have cool tutorials. Like,
yeah, it looks good. We're gonna have to check it out.
Yeah, like endless stuff on the website. I can't even remember where, like looking for the thing where they have their, yeah, all these different sort of oh yeah. Yeah, I love this. You know, this is nice, right? This is where I sort of learned how to do the visualization stuff. Yeah, so this is sort of similar to what we did, right? They're like visualizing, oh, that's what the squeeze state looks like. Rotation gate. You know, you really see that rotating there, you know. but my favorite one is down here. You know, you look at the cubic phase gate. So that's like, this is definitely not a Gaussian operation, because you see it takes a Gaussian state and then just like, whoa, look at all that negative probability. And similarly with this care gate. So yeah, so again, you know, in terms of practicality, I think that the fact that, all I'll say is the fact that these people who are developing photonic quantum computers are emphasizing so strongly that like the Wigner quasi-probability distribution is like by far the coolest way to like visualize this stuff. I think that, you know, speaks to its usefulness. Because if anybody knows, it would be them.
So also, I just wanted to say, I don't know if Moshe is still listening, but
Yes, still here.
right. Okay. So tomorrow, is it 1 o'clock, Moshe?
Tomorrow it's 1 o'clock, yes.
Tomorrow at 1 o'clock, the New York quantum meetup. For those of you just interested in quantum theory,
Young Mills.
we're going to have a discussion on Lie groups and gauge theory, Yang-Mills theory, and Siddhartha Mitra, who's one of our members. He's very smart. He's actually studying to be a medical doctor now. Is that right, Moshe? He's studying?
Not really. He doesn't really study to be a medical doctor. He's doing a PhD in physical biology, in the intersection of physics and biology.
Oh, okay. But he's very smart, you know, mathematically. He taught all of us Lie groups, which I knew nothing about a couple of years ago. He taught us Lie groups, which is essential to understanding, you know, particle physics. And he's gonna go over that. I guess starting from scratch, he's gonna introduce us to that again, and as it relates to Yang-Mills theory. For those of you interested in quantum physics.
Yeah. You know, that reminds me actually, you know, last night I was discovering a couple interesting papers that are basically involved with simulating like both quantum field theory and also string theory on a quantum computer. So like they're, you know, this one, it's a little bit beyond me, I have to say. You know, my gauge theory isn't really where it should be, but here they give, you know, sort of interesting ideas of realizing lattice gauge theory on a quantum computer. You know, this one was like, whoa, you know, towards simulating string theory.
Well, gauge theory is the whole basis of modern physics. There's no way around it.
Yeah, for sure. And it's like, you know, it's just a good example. Oh, and by the way, I was going to mention this for another reason. This paper, A Sparse Model of Quantum Holography, this one, because, you know, when we were talking about our wormhole thing, it was sort of like, hey, can you run this on a quantum computer? Yes, and, you know, if you want to read more about people who have done that, you know, here's a little paper dealing with, you know, doing quantum simulations of the SYK model. And, you know, here's another one where they're like investigating specifically in the ADS-CFT context. Yes, yeah, post these links.
So you believe in string theory? Did you guys sign up for Susskind's lecture at the Simons Foundation?
Oh, no.
Yeah, you better sign up because he's probably closed out by now. Some of you guys, I sent some of you guys I don't think I have your email, Matt, but simonsfoundation.org.
Okay, yeah.
Do you know who James Simons is, as in Chern Simons?
Yeah, I do.
So he's probably the most successful hedge fund manager in the universe. But fortunately, he's done some good with his money, and his foundation subsidizes science research. And Susskind is going to speak a couple of weeks from now. You know, Google simonsfoundation.org events, But he's probably closed out by now. I mean, everybody probably wants to hear him.
No, I think it's still probably open. The important thing to know is that this Simon is exactly the Simon in Chern and Simon theory.
Yeah, yes.
Yeah,
Chern-Simon theory. Yeah, absolutely, yes. I thought I had said that.
And
Of course, I disagree. I disagree with all of Susskind's theories,
So,
none of which have any empirical evidence. But I hope in my next life I'm as smart as he is, so I can do some real work.
Use the force, Luke.
What's that?
Just use the force.
yeah, use the force.
Yeah, I mean, this whole thing with, which I believe Moshe has disproven. Moshe wrote a paper disproving black hole complementarity, which is complete bullshit.
Hey.
String theory, I won't even get into. That's also more of the same. Great math, no empirical evidence.
We'll see. We shall see.
uh,
I mean, I think it'll be interesting to see, like, as those theories, which are so locked up in very, elegant but difficult mathematics, like as, people come up with ways of simulating them on better quantum computers, that stuff will be kind of democratized a little bit, and like people will be able to.
Oh yeah, well, there's no question quantum physics is real. We have empirical evidence for that, but we still don't know. We don't know if gravity is a quantum theory. Yes, everybody believes that it is, and everybody believes that gravitons exist, but show me one. Gravity may not be a quantum theory. I'm not saying we shouldn't pursue it. I mean, I'm not saying we shouldn't pursue string theory. Yes, they're all worthwhile pursuits. But until we have empirical evidence, they're in the realm of mathematics, not physics.
Yeah. Well, when I
case.
say like to be able to simulate those things more easily, on a quantum computer. I mean, it's like you go in to try to like learn some string theory. Like it's pretty hard, you know what I mean? And it's like,
you can simulate it on a classical computer. You can simulate quantum physics on a classical computer.
well, but like
It doesn't mean that it corresponds to the real world.
Well, like barely, like, you know what I mean? Like, that's what I mean. Like, even like the simulations that we do, like, suck. I mean, ultimately, they're just sort of like approximation upon approximation upon approximation because classical computers suck. And it's like, it just seems to me that like, as we get, better and better at quantum simulation, we'll probably be able to find ways of like testing some of these like theories, that were just not obvious because of how difficult it is to even know what the consequences of a theory are. You do a numerical simulation, you can barely do that, spend 40 pages doing some analytical bullshit. Like, it's great. Like, that's what you got to do. But like, compared to like say like I know like everything about spin, you know what I mean? Like I just sit here on my computer and I'm just like looking at that spin do its thing, and it's just like I can simulate it. There's like no surprises, but something like string theory or quantum field theory, they're just so complicated that like you really to do like a visualization of it is impractical. And so you can,
but simulation is mathematics. It's not physics. We can simulate
like knowing what to
we can simulate quantum gravity on a quantum computer, but it doesn't mean that actual gravity is a quantum theory.
I just mean that like in terms of being able to like so fully internalize a theory that like what kind of like experimental predictions it's going to make, like that kind of thing will be easier.
Oh yeah. And the more empirical evidence we have, the closer we are to an actual theory. But in the meantime, and some people say gravity waves prove that gravity waves are predicted by Einstein's classical theory. They're not predicted by quantum theory. So there's no empirical evidence that gravity is a quantum theory. It would be nice if it were.
Yeah.
But being a practical, being an engineer, I need empirical evidence before I believe something.
For sure.
The problem, Michael, is that if indeed gravity is a quantum theory, the empirical evidence, the direct, straightforward empirical evidence will not appear until you get to the Planck scale. So don't hold your breath.
Sorry, until you get where, Moshe? Until you get to...
Scale. You have to get to the Planck scale.
Well, okay, maybe. But there could be indirect ways to show it.
That's what everyone is hoping for, indirect ways.
Yeah.
The direct ways would be to measure space at the Planck accuracy, to measure Planck scale fluctuations in the energy momentum field, in the space-time field.
But again, LIGO's detection of gravity waves is completely classical.
Yeah.
Einstein's equations predict gravity waves. It's a nonlinear effect.
Yeah, of course.
Yeah, it's not. Although you hear people say, "Oh, that shows that gravity is a quantum theory." No,
not at all.
Not at all.
Wait, Jamie, what can you say more about this psi quantum thing? I'm curious.
Oh, sure. Yeah, no, just because Michael's, yeah, I mean, some of the photonic startups in general are just kind of, you don't hear from them. So like Xanadu is cool because, yeah, I got to check some more of those like tutorials and stuff out because that's pretty accessible. So a lot of their like software and code stuff is out there, but yeah, it's hard to get at the photonics hardware because, yeah, I saw, Matthew, you were Googling that. And yeah, there's a lot of money pumping into like psi quantum. But they're in like stealth mode right now, so it's like 250 million or whatever. It's like they were like accounting for like 50% of the money coming into quantum computing startups, but yet they weren't really saying much. So they have some like cool theorists that work there, and that they've been hiring and stuff. But yeah, I
have to say, like, I've never heard of it
all.
Jamie, are they an American company or are they Canadian?
Yeah, it's Silicon Valley. I think. Yeah, they're based in Silicon Valley. I think some of their founders, though, are coming from like Australia and maybe Canada. But yeah, they founded it in Silicon Valley.
Because it looks like, the same old, same old. All you hear about is IBM and Google, who have claimed quantum superiority, which people are challenging. And this sounds like the old, American, we're the best and we're going to keep all the competitors out, which is a problem. This is a political issue more than a scientific issue. Because I had never heard of Xanadu or psi-quantum. You say Xanadu has been discussed on Quantum Appaloosa?
Yeah, it depends. I mean, like Maria Schud is a theorist and she gives talks a lot, and her main like affiliation is with, she's out of South Africa, but she's also works for Xanadu. I think it's part of like the founding people or whatever there.
Yeah.
But yeah, Xanadu has more of a public interface because of all their code and stuff that's out there. But yeah, I mean, it's hard. I mean, like they all are, to get into the hardware, the betas and all that.
There's a lot of stuff going on in India. There's a surprising amount of stuff going on in India. A lot of Terrell's contacts are in India, and it's hard. It's sometimes hard to follow it because they're like, what is it, a 12-hour time difference?
Yeah.
So,
yeah, there's a lot of interest out there too. I know I did the Kiskit Global Summer School, and there was 4,000, and the breakup was 800 people from the United States, 800 people from India, and then it was spread all over the world. But yeah, India and the United States were accounting for most of it.
Yeah.
And I forget what their name was, but there was a Chinese company who had put some qubits on the cloud that I saw.
It might be. I mean, so I have a harder time.
Alibaba.
Yeah, Alibaba is what I was going to say.
Yeah.
Well, the Chinese government is cracking down on Alibaba now. You know, for monopolization. So.
Yeah, I know there's a photonics group that was mentioned in China, but I don't know of the name, so I don't know who specifically the Chinese company is doing photonics.
But
well, yeah, Baidu, that's the other one that I remember.
Yep.
Oh, Baidu? Oh, that's a big company. Yeah. They're publicly traded. I think they're traded on the New York Stock Exchange. Or NASDAQ, or, you know, they're, you know, on an American exchange. But I don't know. IBM and Google seem to be getting all the publicity, and this is an issue. This is, you know, this is a monopolization.
In IBM's credit, it's like you can use it for free. It's really easy.
Oh yeah, yeah. But Google claims to have, you know, done quantum superiority, whatever they call it, and people are questioning that. You know, and it's.
Yeah. Well, I remember the IBM
Google is a big problem.
Like, yeah.
I mean, you know, politically, Google is a very big problem in all of their business ventures. You know, we're just they're trying to monopolize everything.
Yeah. Well,
to change topic, since today we were talking about negative probabilities, and no one is quite sure exactly what is the meaning of negative probabilities. Let me throw in something else that is just as puzzling, at least to me, that I came across recently. This was, I think, last week or the week before meeting of the New York Quantum Theory Group. We were talking about how fast do you cross a potential barrier when a particle goes through a quantum tunnels through a potential barrier.
right.
What is its speed? Now, I don't even have to write down the equations because they're so simple. You start with the Schrödinger equation where the potential is equal to 0. The solution to this is a plane wave where the wave number is proportional to the momentum, which is proportional to the velocity. And the wave number is the square root of the energy of the particle. So basically, the solution to the Schrödinger equation where V is equal to 0 is just the exponential of I times the square root of the energy, and there may be some factors of H or H bar or whatever. Now, if you have a potential, if V is not 0, then in the exponent, instead of having E, you have E minus V, the energy minus the potential. Now, if you have a potential barrier where the potential is bigger than the energy, so basically the energy is not enough to jump over the barrier, then under the square root, you're going to have E minus V. It is going to be a negative quantity. The square root of a negative quantity is imaginary. So now there are two things that are happening. Item number one, because the solution of the Schrödinger equation is e to the I times the square root of energy minus potential. So under the square root, you have a negative quantity. So you make it positive by taking out the I factor. The I multiplies the I that is waiting outside the square root sign. It gives you a minus sign. So you have a negative exponential, which means basically that as you go through the potential barrier, the amplitude decreases exponentially. So the wider the potential, the higher the potential, the faster the amplitude decreases exponentially, which makes sense. This is what I learned in Quantum Mechanics 101 when I was a young man.
Mhm.
Now, if you stick to the interpretation that you get from the Broad's rule, telling you that the momentum is proportional to the wave number. The wave number in the solution to the Schrödinger equation is the square root of E minus V. And the square root of E minus V is now a pure imaginary quantity. So this tells you that the velocity is an imaginary quantity. So now, if instead of an imaginary quantity, you were getting a real quantity, a real number, this would have been even more puzzling, because what you have inside the potential barrier is not a propagating wave function, but a exponentially decreasing function. So no surprise that you don't get a real answer for the velocity. But at the same time, we know that the particle is moving through the potential barrier. For instance, the simplest experiment that I can think of is in this context is the following. Suppose you have a potential barrier, and on one side, let's say on the left side of the potential barrier, you have a neutron. Just a neutron, and you keep it in place, it does nothing. It stays there. After a while, the neutron decays, and you keep looking at the neutron. At some point, instead of having a neutral particle, a neutron, you're going to see a proton, you're going to see a positive charge. You note the time when you saw a proton instead of a neutron. You know that at that time, an electron has left the neutron, and if you happen to see an electron on the other side of the barrier, again, you note the time when you saw the electron on the other side of the barrier, and you know that it took the electron at least this much time to cross the barrier. So you have some measurement of the time it took the electron to cross the barrier. This is you can call it the average velocity of the electron through the barrier. Now, there's no way you can possibly measure the instantaneous velocity inside the barrier, because you can never measure the position of an electron inside the tunnel. You cannot measure it because it does not have enough energy to be there. If you could measure the electron inside the barrier, this would be a violation of conservation of energy. But you can measure the average velocity. You can measure, it took the electron 10 nanoseconds to go from one side of the barrier to the other side of the barrier. How does this relate to the imaginary value for the velocity that we just get very straightforwardly from Schrödinger's equation? I've not been able to come up with an answer. I don't know what an imaginary velocity is. And the thing is, if you look at Einstein's basic equation of special relativity, that the inertial mass of a particle is given by its rest mass dividing by the square root of 1 minus v squared over c squared. You take this expression, you take the square of it, just like the square of it, so the square of the mass is equal to the square of the rest mass divided by 1 minus v squared over c squared. And if v is negative, if v is imaginary, then v squared is negative. So what you have in the denominator is 1 plus some positive quantity, a quantity that is always positive, and you can have v going to infinity, and as v goes to infinity, or v squared, let me say, if v squared where it goes to minus infinity in this case. When v squared goes to minus infinity, then the inertial mass and the energy go to 0. So if you have a particle with an imaginary velocity, the bigger the amplitude of the velocity, the smaller the energy. So it loses energy as the velocity square becomes more and more negative as it goes to minus infinity. This is just straightforward
Sure.
reading
Yeah,
of Einstein's equation. What does it mean? I don't know. I have no idea. If anyone can come up with some thoughts about it, what does it mean? And normally I would say, this is nonsense. This is nonsense. Don't ever waste your time talking about such bullshit. The only reason I am wasting my time thinking about it is because this is the solution of Schrodinger's equation inside the potential barrier. You can get out of it. This is the simplest possible exercise. The very first exercise that we did in quantum mechanics 101, potential barrier. And this is the solution that you get if you take Schrodinger's equation plus the de Broglie assumption.
I think,
yeah.
Moshe, you have to be careful when you're considering, and it's good that you give the comparison with the Schrodinger equation. Because the physics forum, the example of imaginary velocity is actually taking you into something which doesn't make much physical sense, because when you are trying to accelerate a particle, give more and more velocity, you have to put more energy into system. But if you look at, for example, how the metric looks like Lorentzian metric, then you can think about imaginary velocity, and not as velocity, but more like displacement. Then your imaginary displacement would mean that you're not moving along the spatial part, but you're moving in the time direction. And this would make sense in terms, for example, a black hole, you're switching actually the time and space when you go inside the black hole. In a similar way, if you think about the Schrodinger equation and inside of the potential, well, you're not having really a motion like a standard space, and you're not free to really move forward in space. But then when you're inside the well, you're actually free to move a long time. So in a sense that maybe you have to interpret what you're calling imaginary velocity, you have to be careful with the displacement and along what kind of dimension you are moving this displacement.
Huh. That's very interesting. Yeah, I'm gonna have to think about this.
So Matthew, sorry that I missed the beginning, and I really enjoy your crowd here. Unfortunately, I was busy with another meeting, and then I came a little bit too late, and I didn't want to kind of jump into the middle of your presentation. But now I have to go again for another meeting, but I really enjoy your group. I mean, it's a great group. I shared here with somebody was mentioning about the Google and the IBM. So I think John probably was you. So I hope that you enjoy the talk that I gave to the crowd in the Hackadojo last year when the Google came up with their supremacy claim. So
yeah, well, thanks for coming. Thank you for coming.
Yeah, you're welcome, and thank you, everyone. I really enjoy your meetings. Hope to see you again next time.
Matthew, I really appreciate all the effort that you put into preparing this lecture, like all of your lectures. Very clear, very well presented, and I know that lots of effort went into it. So I appreciate it. Thank you.
Oh, thank you. Kind words.
Looking forward to the next session.
Yeah. I'm not even sure what it's going to be yet. But yeah, I have to say, it's like whenever I was learning about this Gaussian stuff a couple of weeks ago, and, it really helps just to be able to like formalize it all out in a notebook, even just for my own sake, because you forget stuff. A couple weeks later, you're like, how did you even do that? It's really helpful to keep a Jupyter notebook record of everything.
Okay, bye guys.
Cool. See ya. Yeah, we should probably all head out. Got to eat some dinner. It's been real. See ya.
Thanks, Matt.
Adios.
Ciao.